Games with perfect information describe situations in which the state of the game is perfectly observable by the players. This is the case, for instance, of chess and checkers, in which every player can observe the board whenever she plays. Instead, in games with imperfect information, players cannot perfectly distinguish the state of the game. For instance, in card games, the player don't know the cards of the opponents. That is, some information related to the current state of the game is private for only some players. The central concept in imperfect information games is the information set. An information set is a subset of decision nodes of a single player that are indistinguishable for such player. For instance, in the picture, suppose that the decision nodes 1.2 and 1.3 compose an information set. As discussed later, this means that player 1 cannot observe which action player 2 has taken at information set 2.1. Graphically, an information set is denoted by connecting all its decision nodes by a dashed or a dotted line, as it happens in the picture. The peculiarity is that the player that plays at a given information set cannot distinguish the nodes belonging to that information set given the history observed so far, where the history is defined as the sequence of actions undertaken by the player and the actions undertaken by the opponents and observed by the player. In order to make the decision nodes indistinguishable for a player, we need that in every decision node of an information set, the available action must be the same. So, for instance, in the picture, we need to change the labels of the actions available to the information set. Specifically, we change from uppercase L3 and uppercase R3 to uppercase L2 and uppercase R2, so to have the same actions in all the decision nodes of the information set. Finally, a player reasons in all the decision nodes of an information set in the same way. This easily follows from the fact that the player cannot distinguish the decision node in which she is. So, when considering the decision of a player, it does not make sense to speak about the decision nodes, but about information sets. Thus, in the game 3, we will not report the labels of the decision nodes, but only those of the information sets. Thus, in the picture, we remove the labels 1.2 and 1.3 from the corresponding decision nodes, and we assign the label 1.2 to the information set that includes both decision nodes. The resulting game with imperfect information is that one reported in the picture. Now we can provide a formal model of an extensive form game with imperfect information. It is a tuple N, A, V, T, iota, rho, key, U, H, in which the tuple from N to U is a perfect information game, while H describes the information structure. Specifically, H is a set, including all the HI, where HI is a set of information sets of player I. Obviously, HI is a partition of the information sets of player I. And each information set is a subset of decision nodes. Some examples of notable imperfect information games are poker games. Consider that the simplest version of poker is the Coon poker, and it is composed of 25 decision nodes, while the Texas Hold'em No Limit poker is composed of more than 10 at 100 decision nodes. We focus on a specific class of imperfect information games that is very important in practice. They are simultaneous action games, that is, games in which each player has only one decision node and no action of the opponent can be observed. A simple example is rock, paper, scissors, where each player can play the rock paper or scissors actions, and the decisions are taken simultaneously. In the picture, player 1 plays first, but her action is not observable by player 2. A different, equivalent interpretation is that player 1 and player 2 play simultaneously, and therefore no player can observe the actions undertaken by the opponents before taking her action. Since every player has only one decision node and cannot observe the actions undertaken by the opponents, the game does not allow any dynamic interaction among the players. We focus now on the problem of perfect and imperfect recall in games. When we introduce information sets in a game tree, we need to investigate which kind of games we are capturing. The first property we could be interested in investigating is the perfect recall of the players. Basically, we have perfect recall when every player recalls all the actions she undertaken in the past and all the actions performed by the opponents that the player has observed. The formal model is the same one of that of an extensive form game with imperfect information, in which the information structure defined by H satisfies some additional constraints, assuring that no player forgets information along the game. This constraint can be expressed as: given any pair of decision nodes of the same information set of player I, say W and W prime, consider the sequences composed of decision nodes and action of player I from the root of the game tree to W and to W prime. These two sequences are those reported in the slide. The first sequence terminates in W, and the last action is AK, and so on up to W0, that is the first decision node in which the player plays along the path leading to H. The second sequence terminates in W prime, and the last action is AL prime, and so on up to W0 prime, that is the first decision node in which the player plays along the path leading to W prime. The constraints to have perfect recall are that these two sequences have the same length, and therefore L is equal to K. The actions are the same in the same order, that is, AJ is equal to AJ prime. The information sets traversed by the players are the same in the same order, that is, WI and WI prime are part of the same information set. Here, a simple example of a perfect recall game. Consider information set 1.2 composed of two decision nodes of player 1. Consider the left decision node. The sequence leading to that decision node is composed of decision node 1.1 and action uppercase R1. Consider the right decision node. The sequence leading to that decision node is composed of decision node 1.1 and action uppercase R1. The two sequences satisfy the constraint discussed before. Consider instead the example in the slide. Information set 1.1 is composed of two decision nodes. The sequence leading to the first decision node is composed only of that decision node. The sequence leading to the second decision node is instead composed of the first decision node and action uppercase R1. So the game in the picture is not with perfect recall. In practice, imperfect recall captures the case in which a player forgets some action played by some players, including herself. In the picture, player 1, when he plays after action lowercase R1 of player 2, has forgotten to have taken action uppercase R1. An interesting question is why we should study games with imperfect recall. In some cases, the game tree may be excessively depth, and one could look for strategies depending on a truncated history. A classical example is patrolling on an arbitrary graph, in which the optimal strategy may depend on an infinite length history. Another example is when modeling humans. They commonly forget some observations. Another issue that may arise when using information set is timeability. Start from an example. Suppose that each player has a timer and therefore they can observe the time passing. If a player has the sense of time, then all the decision nodes of a given information set should be traversed at the same time. Otherwise, a player could recognize the specific decision node she is traversing on the basis of the time the decision node is traversed. In imperfect recall games, the players may have not the sense of the time. Consider the example in the picture. The decision nodes of player set of information set 1.1 cannot be traversed at the same time. Therefore, if player 1 has the sense of time, could recognize that information set 1.1 is traversed at different time. An interesting question is whether non-timeability, that is, the fact that players have not the sense of time, is an issue of only imperfect recall games, and therefore whether in all the perfect recall games the players have the sense of time. The answer is negative, meaning that there are perfect recall games that are not timeable. One example is in the picture. Assume to have the line of the time. Focus on information sets 1.1 and 2.1. There is no way to make players to have the sense of the time when traversing these information sets. If player n, denoting the nature, chooses action phi, that is the left action, we have that information set 1.1 is traversed before information set 2.1. Instead, if nature chooses action psi, that is the right action, information set 2.1 is traversed before information set 1.1. Obviously, we cannot satisfy simultaneously both conditions, except in the case the two information sets are played simultaneously. That, however, is not feasible in a game. Thus, we ask when a game is timeable. To do that, we introduce a notion of chronologically ordered information sets. This notion is based on the adoption of labels. Assign a label to each information set, where a label is a natural number. Each decision node must have a label that is strictly larger than the label of the parent. Information sets are chronologically ordered if and only if it is possible to find an assignment of labels such that, for each information set, every decision node of that information set has the same label. Thus, the labels may have a simple interpretation, that is the time in which the information set is traversed. Consider, for instance, the game with imperfect recall in the picture. We have 4 decision nodes, call Z1, Z2, Z3, Z4 the labels of the decision nodes. In order to have chronologically ordered information sets, we need that Z1 is strictly smaller than Z2, that is strictly smaller than Z4, and Z1 is equal to Z4. That is impossible, and therefore the game in the picture is not timeable. The timeability property is satisfied only when all the information sets are chronologically ordered.